Exercise 17. In this one, we are given a function t on f2, where f is of course some field, and the function is defined like this with this formula, and here alpha, beta, gamma and delta are some fixed field elements. There are two parts. In the first part, we have to prove that this function is the homomorphism of f2 into itself, and in the second one, we have to find a necessary and sufficient, some equivalent condition on these scalars alpha, beta, gamma and delta, so that T becomes an isomorphism, that is, it becomes 1 to 1. So the first part is quite straightforward, that is part A. So we start by considering two vectors and some scalar. Let A be that scalar. We don't have A anywhere here, no? Okay. Then what happens when one calculates this thing? The T image of the sum of these two vectors. By the definition of addition in the vector space F2, this will be x1 plus y1 comma x2 plus y2, and the T image of this will be plus beta times the second coordinate comma, this itself is an ordered pair, gamma times the first coordinate plus delta times the second coordinate. So we have alpha x1 plus alpha y1 plus beta x2 plus beta y2 comma gamma x1 plus gamma y1 plus delta x2 plus delta y2, which of course one can see is true, because we are using, what are we using here? We are using the left distributive laws, left distributive law that is available in the field F. Now this vector can be written as alpha x1 plus beta x2 comma gamma x1 plus delta x2 plus alpha y1 plus beta y2 comma gamma y1 plus delta y2. You can clearly see that if you add these two vectors in F2, you get this one. And the first one of these is nothing but the T image of x1 comma x2, and the second one is the T image of y1 comma y2. So that means T respects addition. And like that, the other one is, of course, we multiply this vector by the scalar A and we calculate the T image of this. So this will be equal to, first of all, we carry out the multiplication inside, we get ax1 comma ax2. The T image of this is alpha ax1 plus beta ax2 comma gamma ax1 plus delta ax2, which is equal to A times. If you really want to be rigorous and show all the details in these calculations, then one can of course use parentheses here, that is use brackets here to separately write alpha and ax1. However, we have not done that because we know that multiplication in the field is associative. So that's why even if we don't write any bracket to when we are writing these products, they are still well defined. Now, using the left distributive law, you can write these components of this vector or the coordinates in this way: A times alpha x1 plus beta x2, again A times gamma x1 plus delta x2, and then again you use the definition of multiplication by a scalar in this vector space F2. Using that, we can write this vector equal to this. So A times, this is the T image of x1 comma x2. So T also respects multiplication by scalar. Hence, T is a homomorphism of F2 into itself. Okay, now next we come to part B, where we have to find a condition on the scalars alpha, beta, gamma and delta, so that if the condition is true, then T is a one-to-one mapping, and conversely also. Okay, now let me first write a sentence and then we will try to understand it. T is one-to-one if and only if its kernel consists of only the zero vector, and that is true if and only if the following system of linear equations has only the trivial solution. This system why? That is because the formula for the function t is this. So if the kernel of t has to consist only of 0, then this vector can be 0 only when this vector is 0. That means when both x1 and x2 are 0. In other words, this system has only the trivial solution where both x1 and x2 are 0. Now from this condition, so clearly t being 1 to 1 is equivalent to this system having only the trivial solution. Now we have to find a condition on the, this is alpha, on the scalars alpha, beta, gamma and delta such that this system has only the trivial solution. Now at this point, if one wants, one can use results from the theory of matrices or results from linear algebra. I mean the part of linear algebra, we are doing linear algebra in a sense because we are solving problems on vector spaces, but the parts that we have not got yet. So we will take the point of view that we don't know anything about these systems of linear equations and their solutions, when they will have trivial solution, when they don't. So we are going to do all the things. Okay, we are not going to assume anything from anywhere. Okay, now our assumption is this. Assumption means first let us define something. Let delta be the quantity, delta means capital delta, alpha delta minus beta gamma. This quantity will be important in determining that equivalent condition. Assume that delta is not equal to 0. why one writes this delta in the first place, the answer to that question is if one really tries to see when this this system of equation has only the trivial solution, exactly how? Of course, the person would try to solve this by the usual elementary algebra techniques that we already are familiar with, that we have learned in school. Namely, you try to eliminate one of the variables. You will see in doing that this quantity becomes important, and in fact whether this quantity is 0 or non-zero, that becomes important. So that's why we are starting like this. Okay, now let us see what happens when this is non-zero. Okay, our claim now is that if this capital delta is non-zero, then this system has only the trivial solution. So that means we now have to show that if x1 comma x2 is a solution to this system, then both x1 and x2 have to be equal to 0. Be a solution to the above system of linear equations. That means now x1 and x2 are not arbitrary variables, they are some fixed elements from F, so that they satisfy both these equations. Okay, then now let's go through this calculation. x1 can be written as 1 over delta times, of course, delta times x1, and delta is alpha delta minus beta gamma times x1. Okay, instead of writing like this, let me do the calculation in the middle as an equation array. x1 is equal to 1 over delta times alpha delta minus beta gamma times x1. So these two things cancel each other and we have x1, and that is possible because we are assuming delta to be non-zero. Right, now the numerator can be written like this: alpha delta minus beta gamma x1 is already there. Along with that, we write beta delta minus beta delta x2. Okay, now what we do, you see, alpha delta x1 plus beta delta x2, from these two things we can take delta common out. So we will then be left with alpha x1 plus beta x2. Like that, from these two terms we can take beta common out. I mean actually minus beta common out. Then we will have gamma x1 plus delta x2 now, because we have assumed that this is a solution to the above system, this is 0, this is also 0, so that means delta 0 minus beta 0, which is equal to 0. So you see that x1, we have shown that x1 is 0. And there will be, you can imagine, a similar calculation to show that x2 is 0. We won't leave that, we will actually show that x2 is also expressible in this form, minus beta gamma x2, and this time the numerator can be written like this: alpha gamma minus alpha gamma x1 plus alpha delta minus beta gamma x2. So this time we can take alpha common out from alpha gamma x1 and alpha delta x2. So then we will be left with gamma x1 plus delta x2, and if we take minus gamma common out from this one and this one, then we have alpha x1 plus beta x2. So just like before, now also this is 0 and this is 0. Okay, so this shows that hence the system beta x2 equal to 0 has only the trivial solution. x1 equal to x2 equal to 0. So this condition that we have, that delta is non-zero, that is a sufficient condition for this system to have only the trivial solution. Now we are going to show that the condition is necessary also. That is, when this system has only the trivial solution, then delta must be non-zero. That is, next we want to show this system has only the trivial solution implies delta is not equal to 0. If we manage to show this, then this will be a necessary and sufficient condition for this system to have only the trivial solution, and equivalently for T to be 1 to 1, and hence an isomorphism. But we will not directly show this implication itself, but rather its contrapositive, which is clearly this. The contrapositive of this implication is this: delta equal to 0 implies the system has some non-trivial solution. P implies Q is equivalent to negation of Q implies negation of P. Okay, so now this is what we want to show. So this will automatically tell us that we have completed the converse. Okay, so that is the strategy. So that means now we will start by assuming that delta is 0, and we will have to produce some actual non-trivial solution, or at least show that a non-trivial solution exists to the given system of equations. Next, assume that delta is equal to 0. Okay. Now what is delta? Delta is alpha delta minus beta gamma. If all of these scalars are 0, then is a non-trivial solution to the system this. Clearly, if all the coefficients are 0, then whatever you put in place of x1 and x2, that will constitute a solution. Because we want non-trivial solutions, so we take both x1 and x2 to be 1. If you want, you can take one of them to be 0 also, but at least one of them should be non-zero, and we have taken 1. Note one more thing, that the exercise does not say anything about the field other than the fact that it's a field. And in the smallest possible case, where the field has only 2 elements, there is a non-zero element, and that is the unit element. So in any case, we can take x1 and x2 to be 1, and this one of course is not the ordinary real number 1, it's the unit element in the field. And we know that in a field the unit element is always different from the zero element. Okay, so this is a very special case. So now that we have handled this case, we can assume that one of these four things, alpha, beta, gamma and delta, is non-zero, at least one of them. And we are going to write like this. So we now assume without loss of generality that alpha is not equal to 0. But how without loss of generality? You can tell me what happens when beta is say non-zero and the others are 0, suppose. The answer to that is this. You see, the justification for assuming that the first one is non-zero is this. If beta happens to be non-zero, the non-zero one, then you just simply rewrite the system like this. This is also a system of linear equations where you can treat this variable as say y1 and this one as y2, and you can rewrite this entire system like this: alpha prime y1 plus beta prime y2 equal to 0, then gamma prime y1 plus delta prime y2 equal to 0, where alpha prime is beta, beta prime is alpha, gamma prime is delta, and delta prime is gamma. So essentially you are again having a system of equations where the first one is, the first coefficient is non-zero. The way we have written the system, in the first equation the first coefficient is non-zero. And you can imagine that same thing will happen if, for example, gamma turns out to be the one that is non-zero. In that case, we don't even have to do this much. We just switch the positions of these two equations. We write gamma x1 plus delta x2 equal to 0 and alpha x1 plus beta x2 equal to 0. So this again then becomes a system of equations where the first one is non-zero. And a similar one if delta turns out to be the non-zero coefficient. There you have to not only change the positions of the equations, but you have to change the variables also, positions of the variables. So in any situation, no matter which one is non-zero, you can bring the system into a form where the first one is non-zero after rearranging things. So that's why, and you can imagine that these coefficients are not special. They are symmetric with respect to their positions in this system. In this sense, gamma is a coefficient of x1, alpha is a coefficient of x1. So if you think of gamma in place of alpha and alpha in place of gamma, of course you are not, I'm not telling you to just simply write gamma here and alpha here. Just imagine that they are just coefficients of x1, and just like that beta and delta are coefficients of x2. There is no special distinction between beta and delta. Just like beta is a coefficient of x2, delta is also a coefficient of x2. and there is nothing special about this variable x1 itself. One in its place one can think of x2 also. So what I am saying is that whatever we are going to do after this have exact corresponding things in the other cases where beta is non-zero or gamma is non-zero or delta is non-zero. That's why we are able to write assume without loss of generality that alpha is non-zero. Do you see how useful the concept of symmetry is? It is because of the symmetry of this system of equations that we are able to drastically cut down on the calculations. We don't have to do that many repetitions. They will be essentially repetitions. If you do another one which corresponds to the case beta is not equal to 0, that is going to be exactly similar to this. So this concept of symmetry, that's why symmetry is very important not only in mathematics but in many sciences also, particularly in physics. And that's why group theory is so important, and it keeps appearing in many different parts of science and in many other places also. Wherever there is symmetry, you will find groups. Okay, so now alpha is non-zero. Then one can verify that x1 equal to minus beta divided by alpha and x2 equal to 1 is a non-trivial solution to the system. If you don't like to write the system again and again, you write the system of equations the first time we write it and give it some sort of number. Then you can refer to it using that number. Plus delta x2 equal to 0. So we see that when capital delta is 0, then in any case the system of equations has a non-trivial solution. Equivalently, if the system of equations does not have any non-trivial solution, that is, it only has the trivial solution, then delta must be non-zero. Thus, if and only if the above system has only the trivial solution, and correspondingly if and only if t is 1 to 1. That is, this is a necessary and sufficient condition for T to be an isomorphism. Those of us who know about matrix, almost all of us know, this delta is nothing but the determinant of this matrix. If one writes this system of equations in matrix form, then instead of writing these two equations, one can at once write a single matrix equation that looks like this. This is the matrix of coefficients, and its determinant is our capital delta. Or in a more brief manner, if you are denoting the matrix by A and this column of variables by X and the 0 column by 0, then this is our matrix equation. And we know that this equation has only the trivial solution x equal to 0 if and only if this matrix is invertible, that is, if and only if its determinant delta is non-zero. Because we are assuming that we don't know about these things, so we are doing things like this. Actually, we know, we have got these things before. In fact, in our school courses, we have got these elementary things. At least for 2 by 2 and 3 by 3 matrices, we know about determinants and what role they play in solving such systems of equations. But we are taking the point of view that we are not following those developments. Okay, we have got to know about these things from our previous courses somewhere in our schools, but right now we are developing everything from scratch. So that's why this we will again come across in its most generality when we learn about matrices in this book itself later on when the time comes. The next one is essentially this exercise itself, but there is one more variable. That is, this time instead of f2 we will have f3, and it's going to be slightly complicated. Okay, so the solution ends here. Let T be defined on F3, just like before. F is any field by a formula that looks like this. Alpha 11 x1 plus alpha 12 x2 plus alpha 13 x3, comma alpha 21 x1 plus alpha 22 x2 plus alpha 23 x3, comma, because we should have again a 3 vector alpha 31 x1 plus alpha 32 x2 plus alpha 33 x3. Okay, so that's how we have defined this function on F3, and it's understood that these alpha ij's are all coming from the field F. Show that T is a homomorphism of F3 into itself, and determine necessary and sufficient conditions. On the scalars alpha, I need ink. On alpha, I just saw that T is an isomorphism. The part that will show that T is a homomorphism is just like the previous one. We have only one more variable and there is a sameness to the calculation, so that I will leave to you. This is one of the big advantages of vector spaces. A space with, I am prematurely using this, with 2 dimensions is almost the same as a space with several billion dimensions, as long as the things you are dealing with are linear. So essentially what is happening, we have one more variable and the number of components has increased by 1 in the vector. So instead of dealing with 2 components, now you will be dealing with 3 components. So that's just about what you will have in trying to show that T is a homomorphism. So that part we won't do. We will instead try to find this condition. Or instead of using the word easily, one can routinely verify that T is a homomorphism, which means that you know what to do. There is no twist here. Now define. Okay, this time also we are going to define one delta, but this delta will be somewhat long. Alpha 1 1, alpha 2 2 alpha 3 3. Since everything ultimately comes down to some determinant, so in this case also what we are going to write here is going to just be the determinant of this matrix. And you can see that the coefficients have been numbered in that way also. This becomes the first row, first column element in this matrix. This becomes the first row, second column element in this matrix, and so on. Okay, so let us write the expression for delta. We don't know about determinants. Our thing now is that we have this delta which we have figured out from trying to find a condition for the system of equations. In this case also we will have a system of equations in trying to find a condition that that system has only the trivial solution. From that search we have found this delta. Alpha 1 2 alpha 2 3 alpha 3 1 plus alpha 1 3 alpha 2 1 alpha 3. I should be extra careful in writing this part. 1 1 2 2 3 3 1 2 2 3 3 1 1 3 2 1 3 2, then minus alpha 1 2 2 1 3 3 minus one 1 2 3 3 2 minus 1 3 2 2 3 1. Okay, so this is our delta. Clearly T is 1 to 1 if and only if its kernel consists only of 0 if and only if the following system of linear equations has only the trivial solution. This time let's write the equations one below another. Alpha 1 1 x1 plus alpha 1 2 x2 plus alpha 1 3 x3 equal to 0. 2 1 x1 plus alpha 2 2 x2 plus 2 3 x3 equal to 0. then 3 1 x1 plus 3 2 x2 plus alpha 3 x3 equal to 0, and this time let us call this system 1. Okay, so we are going to start our calculation now. So first we assume that our big delta is not equal to 0. Then one of these things must be non-zero. Alpha 1 3, alpha 2 3, alpha 3 3 must be non-zero. But why? If alpha 1 3, alpha 2 3 and alpha 3 3 are all equal to 0, then delta itself will be 0. Why? In the first term you have alpha 3 3. So suppose that all of these scalars are 0. So here you have alpha 3 3, so this becomes 0. Here you have alpha 2 3, this becomes 0. Here you have alpha 1 3, so this one becomes 0. What about the minus terms? Here you have alpha 3 3, here you have alpha 2 3, and here again you have alpha 1 3. So that's why one of them must be non-zero. Assume without loss of generality that alpha 1 3 is non-zero. If you ask me again how without loss of generality, in this case also you will see that if one of the others is non-zero, one of the other two is non-zero, then we essentially get a case that is exactly similar to this one. And as far as these coefficients are, or these scalars are concerned, you can see that the expression delta is symmetric, or the positions of these scalars is symmetric in the sense that if you take a permutation of these scalars, if you for example interchange the positions of alpha 3 3 and alpha 2 3, you interchange their values, nothing essentially changes. And that again comes from the fact that one can rearrange these equations in the manner that we discussed in the previous solution. So the point here is that we can assume without loss of generality that alpha 1 3 is non-zero. Okay, now what do we get from that? Now from the equations in 1, we get alpha 1 1 alpha 2 3 minus alpha 1 3 alpha 2 1 x1 plus alpha 1 2 alpha 2 3 minus alpha 1 3 alpha 2 2 x2 equal to alpha 2 3 times 1 1 x1 plus 1 2 x2 plus 1 3 x3 minus alpha 1 3 times alpha 2 1 x1 plus alpha 2 2 x2 plus alpha 2 3 x3, and this is equal to must be non-zero without loss of generality. Before this line we forgot to start properly. Let x1 comma x2 comma x3 belonging to f3 be a solution to the system of equations 1. Okay, that has to be written before writing this, and because this is a solution, this is going to be 0 and this one is also going to be 0, so we get 0. Let's see this step also. Do we really have this equal to this? Alpha 2 3 alpha 1 3 x3 minus alpha 1 3 alpha 2 3 x3. So these two terms cancel each other and we are left with alpha 1 1 alpha 2 3 x1 minus alpha 1 3 alpha 2 1 x1, then plus alpha 2 3 alpha 1 2 x2 minus alpha 1 3 alpha 2 2 x2. Yes, and there is another similar one, which is this alpha 1 1 alpha 3 3 minus alpha 1 3 alpha 3 1 x1 plus alpha 1 2 alpha 3 3 minus alpha 1 3 alpha 3 2 x2 equal to this time this is going to be equal to alpha 3 3 times alpha 1 1 x1 plus alpha 1 2 x2 plus alpha 1 3 x3 minus alpha, I am totally depending on what I have written here. So if you spot any mistake, please let me know. 3 1 3 2 3 3. At least we are in a part where we can in fact instantly verify the steps. So let's just do that. Let's be sure. Alpha 1 1 alpha 3 3 x1, okay, plus alpha 1 2 alpha 3 3 x2, alpha 1 2 alpha 3 3 x2, okay, minus alpha 1 3 alpha 3 1 x1, alpha 1 3 alpha 3 1 x1, minus alpha 1 3 alpha 3 2 x2. And these two things, when we multiply them by these, they cancel each other. 1 3 3 3 1 3 3, yes. And then again, because x1 comma x2 comma x3 is a solution to our system, so this is 0 and this is also 0. Which imply now note that we have got two equations in x1 and x2. One of them is this times x1 plus this times x2 equal to 0, and the other is this times x1 plus this times x2 equal to 0. Now suppose we want to eliminate x2 from these two equations by the usual elementary algebra procedure. So which imply, so for eliminating them, what should we do? Here we have one coefficient of x2, here we have the other. So we multiply this equation by this one and this equation by this one, and since and subtract them, okay. So if we do that, we get alpha 1 3 x1 delta will be this, alpha 1 2 alpha 3 3 minus alpha 1 3 alpha 3 2 times so this one is this, so by this we are multiplying this one, alpha 1 1 alpha 2 3 minus alpha 1 3 alpha 2 1 x1 plus 1 2 2 3 minus 1 3 2 2 x2 minus, we multiply this one by this one, alpha 1 2 alpha 2 3 minus alpha 1 3 alpha 2 2 times this one. Plus 1 2 3 3 minus 1 3 3 2 x2. It turns out, this of course I am not going to do, verify here itself, that this thing, one thing is for sure, there will be no x2, because that's what we are doing here. No, after forming this expression, the terms containing x2, they will cancel each other, but whatever we are left with From that you can take alpha 1 3 common out, and x1 of course is there outside. After taking alpha 1 3 common out, inside you will have an expression involving the alpha ij's that will turn out to be equal to this delta. This you please verify. I have done it today again. This is an old solution that I wrote. But today I actually verified that this becomes equal to delta, but you also please do it. Okay, so that means and this is going to be equal to 0. Why? Because this is 0, this one is also 0. Now, according to our assumption, alpha 1 3 is non-zero and delta is also non-zero. Since are both non-zero, we have x1 equal to 0. So x1 must be 0. Now system 1 reduces to this because x1 has been proved to be 0. So the equations in system 1 now look like this. And let us call this reduced system 2. Okay, if alpha 2 3 is not equal to suddenly why are we considering that this is non-zero? You will see why, but we will also deal with the other case when alpha 2 3 is 0. Okay, so if alpha 2 3 is non-zero, we can similarly show that x2 is also equal to 0, and this similarly you can imagine is a big similarly, but it can be done. I have actually seen that it happens. When alpha 2 3 is not equal to 0, then one can similarly, just like how we have shown that x1 is 0, one can show that x2 is 0. One can recognize the similarity and not do the actual calculation, but I have actually gone through the calculation and one gets x2 equal to 0. Okay, so under the condition that alpha 2 3 is non-zero, we have x1, already x1 is 0 for us, now x2 is also 0. Then the first equation of system 2 reduces to alpha 1 3 x3 equal to 0. This implies x3 is equal to 0. Why? Because we already are under the first assumption that alpha 1 3 is not 0. Okay, that we assumed without loss of generality, that thing. So x3 is 0. So you can see that we have managed to show that x1, x2 and x3, all of them are 0. But keep in mind, this is under the condition when alpha 2 3 is non-zero. Now we also have to look at the case where alpha 2 3 is 0. Now assume alpha 2 3 is 0. Okay, now under this again, if alpha 2 2 is 0, then okay, if alpha 2 2 is 0, then okay, let me write it below here. Alpha 2 1 times alpha 1 3 alpha 3 2 minus alpha 1 2 alpha 3 3 is equal to delta, and hence this is not equal to 0. If alpha 2 2 and alpha 2 3 are both 0, I mean that is the case that we have right now. You go to the expression for delta, the definition of delta, you will see that from the terms that survive, two of them survive, they give you this expression. So from our initial assumption that delta is non-zero, this now becomes non-zero. This implies keep in mind this is non-zero, not equal to 0. Since this is non-zero, both alpha 2 1 and this one must be non-zero. We need non-zeroness of this one, this expression. Not equal to 0. Okay. but then by the solution to the previous exercise, that is exercise 17, the system consisting of these two things, I think the first two equations here in system 2, alpha 1 to x2 plus alpha 1 3 x3 equal to 0, comma alpha 3 to so first and third has only the trivial solution. So you can see that after showing that x1 is 0, this is one case. In this case, we have shown that x2 is 0 and x3 is also 0. And now, in the other case, where alpha 2 3 is 0, there also we now have to consider two cases. We are in one of them right now. Alpha 2 2 is 0. In this sub case, we come across the fact that this expression is non-zero, and this expression turns out to be the delta that we had in the previous solution for this system, consisting of the first and third equations from system 2. So because the delta, in fact you can see alpha 1 2, alpha 1 3, alpha 3 2, alpha 3 3. If we really go to the coefficient matrix of this system, the determinant of this will be what? Do we not have that thing here? We have the negative of that, but it does not matter. We need only non-zeroness. So alpha 1 3, alpha 3 2 minus alpha 1 2, alpha 3 3. So that's why this system of equations, or this subsystem, in fact let us just call it subsystem, has only the trivial solution. That is, in this case also both x2 and x3 are equal to 0. So we did not have to repeat the calculations. We are effectively being able to use what we did in the solution to the previous exercise. So this case is also handled, and in this case also we are getting x2 and x3 both to be 0. And now we have to assume that alpha 2 2 is non-zero under the assumption that alpha 2 3 is 0. Next, assume that alpha 2 2 is non-zero. Then the second equation, of system which is, so let's now look at the second equation. Alpha 2 3 is already, I mean we are under that assumption, so this term is not there, so we only have alpha 2 to x2 equal to 0. Now because of our new assumption, x2 must be equal to 0, implies x2 is equal to 0. So now x2 is 0, so we can use the first equation, which will become alpha 1 3 x3 equal to 0. And keep in mind, in the beginning itself alpha 1 3 is non-zero, that we have assumed without loss of generality. Thus the first equation of system 2 reduces to, let's not wrap this part off, not yet. So now the first system, because x2 is 0, the first equation of system 2 becomes alpha 1 3 x3 equal to 0, which implies x3 is equal to 0. You can mention, since it's been some time, we have mentioned this. So in this case also x2 and x3 are both 0, and we are not, nothing else is left. We have actually seen all the cases. If you go through all the things carefully, you will see that all the cases and sub cases have been covered. So we see that in any case we have this. So that means our assumption that our capital delta is non-zero has led us to the conclusion that our original system 1 has only the trivial solution. Okay, so that is one half. Now we look at the other half. Thus, but before going to the other half, let us conclude what we have finally got. Thus, not equal to 0 implies has only the trivial solution, where by trivial solution we mean that all the components are equal to 0. Okay, now just like the previous solution, we are going to assume that delta is equal to 0 and then show that the system 1 has a non-trivial solution. equal to 0. If all the, just like before, if all the coefficients are 0 for all possible I and j, then this is a non-trivial solution to system 1. So assume without loss of generality that alpha 1 is not equal to 0, which again is justified by those symmetry considerations. If anything else is non-zero, then you rearrange the equations accordingly to make that thing the first one. In maybe another system which is just the given system but rearranged in a different manner. Okay. If alpha 1, alpha 2 minus alpha 1 alpha 2 is not equal to 0, then one can verify these solutions took time. Okay, it's not that one day I just suddenly sat and started writing the things. I made several mistakes, I forgot about cases, and this happened for a long time, and then finally I came up with this solution which given the complexity of the thing may have some error, okay, but it takes time to find this kind of things. Then at least for me, okay, then one can verify that x1 equal to alpha 1 is going to be somewhat large, alpha 1 alpha 2 minus, I hope these things are feasible, alpha 2 minus alpha 2 alpha 1 minus alpha 1 times 1 minus 1 running out of space, minus 1 this is 1 okay, divided by this x2 equal to 2113 minus 2311 divided by this quantity minus alpha 1 to alpha 21 comma, this is not looking good, times, let me write it here, alpha 1 1 alpha 2 2 minus alpha 1 2 alpha 2 1 comma x3 equal to 1 is a non-trivial solution. Okay, non-trivial solution to system 1. This of course I have not recently verified, so I would urge you to do this for me. So what you have to do, you have to put these expressions in the 3 equations in system 1, and in each of them you will get 0, and in doing so somehow this assumption that delta is equal to 0 will be of use. And why is this solution non-trivial? Because see, we don't really know whether x1 or x2 or both of them or none of them is 0, but x3 at least is non-zero, so this solution is non-trivial. A similar condition arises if one of the following expressions is non-zero, and these are the expressions. 2233 minus 2332, then 2133 minus 2331, 2132 minus 2231, that means non-zeroness of any one of these expressions, there are more I am going to write now, will lead you to a similar non-trivial solution. Two one three two 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 three one 1 2 3 1 2 3, then 1 2 3 3 minus 1 3 3 2, 1 1 3 3 minus 1331, 1132 minus 1231, 1223 minus 1332 and 1123 minus 1321. If any one of them is non-zero, just like this one has been assumed to be non-zero, then one will similarly get a non-trivial solution. So we can assume that all of them are equal to 0. None of them is non-zero. So we assume that all of them are 0, including this one. Okay. Then under this new assumption, one can verify that x1 equal to minus alpha 21 divided by alpha 11, comma x2 equal to 1, comma x3 equal to 0 is a non-trivial solution to our system 1. To show that this is a non-trivial, although in this case the expressions for x1, x2 and x3 are very easy, that's why showing that they satisfy the equations, the three equations in system 1, is it's going to require a lot, and that a lot is provided by this assumption that all these expressions are equal to 0. That will allow you to prove that these things actually give you a solution to system 1, and it's also non-trivial because x2 is 1, which is non-zero. Note that this assumption that all these expressions are 0 can be made because in the other case where at least one of them is non-zero has been handled. Okay. So that's why we have now actually gone through all the possibilities. Thus, if delta is equal to 0, then system 1 has a non-trivial solution, or equivalently, if system 1 has only the trivial solution, then delta must be non-zero. We have thus shown that delta is not equal to 0 if and only if system 1 has only the trivial solution. If and only if T is 1 to 1. As the temperature is again rising, the lizards are going to disturb. They can't do anything about it. I don't want to kill these things. Okay, so if and only if T is 1 to 1. So again, this new delta, its non-zeroness is our necessary and sufficient condition for this second T to be an isomorphism. Now one question arises, of course, having seen all these things, why do we have to go through all these extremely ugly calculations? There is no beauty in these things. These are undoubtedly very ugly looking. Why can we not just use the things that we know about determinants and just simply claim that because we know that system 1 has non-trivial trivial solution if and only if delta is non-zero, so that's just it, that's the end of story. The reason for going through all these things is that this is how we should go actually. And why is that so? That is because, fine, say you claim you know that result, that system 1 has only the trivial solution if and only if delta is non-zero. How do you know that? You had to go through something to know that, right? So that something is this. So it will, if not anything, it will refresh those parts. Of course, this may not be the most efficient way. It's hardly an efficient way to actually verify that the determinant is non-zero if and only if a system of linear equations is having only the trivial solution. But it is one of the ways. It's, you can view it as something that a student will come up with if he or she is struggling with this thing without any help from outside, without looking at something advanced. Okay, so that gives you an another purpose of going through these calculations is that it tells us what sort of complexity we can expect if we say try to go to F4 or F5. You will soon realize that this quickly becomes unmanageable. Even in the case 3, it is extremely vast and many things we had to just say we can verify that this is true, one can verify that that is true. But when one tries to transition from 3 to 4, there is no clear way of doing that in a very neat manner where things become routine in a sense that one can write a computer program and then tell the computer to perform these things. The first obstacle is figuring out what delta is actually. In the first case where we had 2, where the dimension is 2, delta was something. In dimension 3, delta is something else. In dimension 4, delta again is going to be something else. So this type of exercises have been given here for the purpose of what can I say? For the purpose of bringing this question in your mind. What is so special about this delta? Then when you later encounter determinants, there you see that this delta that you somehow found in these solutions is actually something quite important. That's how things are supposed to go according to Herstein, which is of course not always possible for us. Sometimes we are in our solutions prematurely using some things that are way ahead of us at that point. But at least in this case, we can see that we have gone through the things the way Herstein assumes us or prefers us to go. So that is a justification for these solutions. But of course, you can, if you want, you can go through it carefully, and you may be able to still compress the solution, or you can try to come up with some clever solution which does not need these things and still gets the job done. I mean, of course, delta should be there, but the way of showing that delta should be non-zero, that is a necessary and sufficient condition, that is not necessarily only this. You may come up with something very clever and short. Who knows? Maybe that is something really interesting. And so this solution ends here itself. And let us solve another one. This, don't be afraid, this is not the case 4. I cannot handle that this way. It is something else. Let T be a homomorphism of V into W. Using T define a homomorphism T star of this into this. Let us first see what we have to do. We are given two vector spaces, V and W, which are vector spaces over the same field, of course, which is F. There is some field F, and it is given that T is a homomorphism from V into W. Now, using T, we have to somehow define a homomorphism from this space into this space. What is this space? This is the space of all homomorphisms from W into F. Okay, so things here look like this. And things here look like this. Okay, there are all the homomorphisms with domain W and codomain, if you want to call this that codomain, F. And this has all the homomorphisms with domain V and codomain F. These themselves are vector spaces. We already know this. Okay. So that means if you are choosing something from here, say some F, you want somehow that F to get mapped onto a homomorphism from V into F. Now, before you think of homomorphism, let us just simply think of the mappings. So your input of the map T star will be some F from here. So that means that will be a function that looks like this. Okay, and you want a function from V into F. Do you see what that function is going to be? I mean, one natural function from V into F using these two things. Why not take their composition, which is it going to be T composition F or F composition? T composition F, because we are consistently writing mappings to the right of the argument. So the order in which they appear, that's how their composition should be written. So this is a mapping from V into F. So this is our clue. So let us now use this clue to set up the map T star. We define by F T star equal to T composition F. Note that for any F belonging to this, F is a mapping of W into the underlying field F. Hence, T composition F is the mapping from V into F. That is because this is F, this is T, and this is T composition F. So when we apply T composition F to some vector from V, first T takes that vector V to Vt, a vector in W. To that, when we apply small f, we get a scalar in the field. So all in all, we get a vector in V gets mapped onto a scalar in the field. So if nothing else, this is a function from V into F. Now we need to show that this is actually not just simply a function but also a homomorphism. Actually, there is nothing to show. We have already seen this before. Have we seen this before? Composition of two homomorphisms is again a homomorphism. I mean, for vector spaces. Let us just do it. Let us take two vectors u and r, v1 and v2 in V and a scalar alpha in the field F. Then v1 plus v2 T composition F is equal to, by the definition of composition of mappings, it's going to be this. Now since T is a homomorphism, so T respects addition, so we get v1t plus v2t, and F is also a homomorphism from W into F, so F also respects addition. Again, use the definition of composition, you get this. So T composition F respects addition, and alpha v1 T composition F equals alpha v1 T F. It also respects multiplication by scalar, and so does F. Hence, T composition F is a homomorphism from V into F. What have we shown? We have just simply shown, even after doing so much, that the image of F under T star is actually an element in the second set. Since for this T composition F is unique, T star is well defined. We have just shown that the function T star is well defined, but now we have to show that T star itself is a homomorphism. For that, let F1 and F2 be two elements or vectors in the domain of T star, which is hom W, F, and we will need a scalar beta. Okay, do we need to oh yes, we will be needing that also. What shall we need actually? V, okay. Comma beta belonging to F and in an arbitrary vector V belonging to V. Then V F1 plus F2 T star. Does it make sense? T star F1 plus F2 is going to be an element here. That means this entire thing is a homomorphism from V into F. We want to see what the homomorphism does to an arbitrary vector in V. By the definition of T star, this is T composition F1 plus F2. By the definition of composition, this is Vt F1 plus F2. Now, by the definition of addition in this space, this is equal to Vt F1 plus Vt F2. T composition F1 plus V T composition F2. Here we have in this step just used the definition of composition. Again, by the definition of addition in this space, T composition F1 plus T composition F2. So whatever this homomorphism from V to F does to V, this also does the same thing to V. So that means since V is any vector in capital V, so these two functions are identical. Which implies F1 plus F2 T star equal to T composition F1 plus T composition F2, but this is F1 T star and this one is F2 T star. This proves that T star itself respects addition, and like that there will be a calculation involving multiplication by scalar. By the definition of T star, this is T composition beta F1. We now apply this composition on V1 in two steps, of course. First Vt, then beta F1. This is equal to beta Vt F1. What is this step? In this step, we have applied the definition of multiplication by scalar in this space, V, F. To multiply F1 by beta means this. Okay. Now inside we have T composition F1 applied to V. Again, by the definition of multiplication by scalar in this space, this thing is this, which implies since these two functions have the same effect on any vector v in capital V, so the functions are identical. Beta F1 T star is equal to beta T composition F1, which is beta F1 T star. Hence, we can now finally say that T star itself is a homomorphism. This homomorphism will be, this particular one will be important when we study linear functionals, which are homomorphisms from a vector space into its underlying field. That is, homomorphisms where the inputs are vectors and outputs are scalars. They have different types of names also. For example, in you can ask a question like this: in a room, what is the temperature at this point? In a given at a given instant, what is the temperature at this point? So the function that tells you about this temperature has as input the point, which is a vector, which can be given by coordinates, and the temperature value is a scalar. I am not saying that it's a linear functional or a homomorphism, just giving you an example of such a function whose input is a vector, output is a scalar. They are often also called scalar fields. Hence, T star is a homomorphism. So this completes the solution. Two more are there, 20 and 21. So that we will do in the next video. So that will be all for tonight. Tomorrow we have Galilean's exercises, but groups we have done recently, so that means tomorrow rings from Galilean. So that's just it. So until the next video, this is me, Lucifer, from a mathematical room. Have a nice night.